see, I'll put a little of that derivation up. I just sketch it, the result, and then we'll spend a couple minutes just with elementary solutions of the wave equation. That's what we're talking about. So, in terms of the little review, it would go like this. The first thing would be that we had that very long chain of masses on and on and on. And we have mass, K, mass, etc. We had a J plus 1, J minus 1 mass in position. And then we eventually use the delta x as that little separation distance. So that was everything. And then the Lagrangian looked something like this. Sum of 1/2 m x I dot squared minus sum over 1/2 k x I plus 1 minus x I squared. I'll ignore any other details. And then we did the Euler-Lagrange equations. We had m x j double dot equals k x j plus 1 minus 2xj plus x j minus 1 for all the j's. And then the grand result of this was 4. We ended up getting, 4. Realize x of j be equal to u of x of j and t. And we finally ended up with d squared u dt squared plus k delta x squared over m d squared u dx squared. And then I showed that when we take the masses, divide them in half, and distribute them on the midpoints of the springs, that this constant remains unchanged. So that's as far as we got. So we had k delta x squared over m. It actually equals constant equals d squared. We do it right. So I'm just going to write here limiting process. Limit process. There you go. And now we have our wave equation that we can study a little bit. And people who have ambitions to simulate this thing numerically, give this thing a try. And you have to be careful if you want to be sure you do it right. You have to be careful with the endpoints. So I didn't include the endpoints here. Right? The end masses only have so there's this, probably this would be, k equals 2 to n minus 1 type of thing.
I guess you can make it like go out of the screen, the endpoints, so it appears infinite.
That's right, you can make it infinite, or you can somehow do some periodic boundary conditions where you identify this one with that, with the first one. It terms of its differential equation. But yeah, if you had enough of these, you should be able to observe wave type behavior. Good. So let's go ahead and study this a bit more. This is something you'll see a lot of in future. B squared u dx squared. That's the one-dimensional case. Have you guys seen the three-dimensional version where you have a del squared operator? Let me write it down for you in one dimension. In three dimensions, what we do is our d squared over dx squared is turned into, and this is Cartesian coordinates, is turned into d squared x squared d squared over dy squared d squared over dz squared, so not equal plus. And this is referred to as the del squared operator. You can think of it as the scalar product of the gradient operated with itself.
Isn't it called like Laplacian, I think?
Yeah. There's different names here. This thing is sometimes called Mabla, and in the German and Russian literature, I know this del squared is referred to as just delta. Okay, so you run into different versions of this. This one here, I'll just put as a note, then we're going to return to one dimension. If you had, if gradient equals d over dx I hat, I make some room here. Just wondering if you guys have seen these things before. Plus d over dc k hat. You guys seen this before as the gradient? Yeah. Yeah, okay. Then what would gradient squared be? Then gradient dotted into itself, or I'll just say squared, would be equal to this over here, right? That's what you would get. Because the I hat would only go with the I hat and so forth. So yeah, that is in three dimensions. And in three dimensions, your wave equation looks like this. D squared u dt squared equals v squared del squared u, for that reason. And u equals u of x, y, z, and t. So yeah, you just want to have that all there in the background. So you've seen it before and you're going to see it again many times. In fact, a bunch of the vector analysis you guys have learned, like learned div, grad, curl, and stuff, that all comes into play when we're talking about wave equations and their solutions. So yeah, you've got a lot to look forward to. Are you guys at 107 yet? No.
Yes.
You are, 107A, yeah. Okay, yeah, then you've actually been seeing quite a bit of this, and next semester, 107B is where you'll really hit the wave equation material. Good. That's the way to do it. So what does this tell us about, after all, we have this object right here, that chain of masses on rings. So what does a solution to this look like? And there's the simplest solution. Of our wave equation. It's a u of x and t. That's staying way back there. Equals use another letter. F of x plus or minus t times t. So there's a partial differential equation. solution has the form of a function of one variable. And this function of one variable, the argument is x plus or minus b times t. What you do with this is go into the wave equation and see what happens. We'll just work right underneath. We'll just work right underneath the wave equation here. So what is the second derivative with respect to time? The second derivative with respect to time, you've got a chain rule. Actually, let's do them one at a time. So du dt equals f prime of x plus or minus dt. And then with the chain rule, we get times plus or minus v. And then we do the second derivative. And v is a constant, so we're just having f double prime x plus or minus dt. And then plus or minus v squared, which just gives us equals v squared f double prime of x plus or minus dt. That was the left-hand side. Left-hand side. What about the right-hand side of this equation? No. Now, the right-hand side, b squared u dx squared is equal to b squared. And now, two space derivatives are just f double prime. F double prime of x plus or minus dt. So, I can put a check mark beside both of these. They're equal, and that's what it means to be a solution of the wave equation. So I just proved that any function of this form is a solution of the wave equation. So, boom, any function. Any function f such that f of x, this is right, any function f of x plus or minus dt solves the wave equation. Good. Now we have to go back and ask, yeah, what does this mean? What does a function of that argument look like? And opening up some space here. Let's just consider f of x. If f of x is just going to be a pulse of some kind, that's f of x. Now if I replace this argument with x plus, or I'm sorry, with x minus dt, then it just means that this pulse is moving with the speed v. Because suppose this is f of x minus dt, and I say t equals 0, right? That's just f of x. Then are exactly the same, then this here, x minus dt equals 0, right? This was x minus dt equals 0 at the origin. The origin and t equals 0. So now right here, this is for t equals x over e. It just means it's moving to the right. So whatever this pulse was, consider a pulse, I'll just call it a pulse, smooth function. At time t is equal to this distance x over b, I'll call it x1. Call this point x1, t1 equals x1 over b. The pulse is moved to the right. With speed, and therefore, pulse moving to the right with, so we have a pulse moving to the right. Moving in positive x direction with speed v. So now, if we did that x plus vt, it would be moving to the left. And so that's the meaning of the really basic meaning of the wave equation. It describes something that propagates. This could be a stadium wave, I'm told. I've never been in a stadium with a wave, stadium wave, but good. So if, or I'll just write and f of x plus bt is the pulse moving to the left. Left with speed v. And of course velocity minus v. So yeah, in this sense, you just take any function whatsoever, statically defined, and then just replace the argument with x plus or minus dt, and that thing is a solution, something moving right or left. But that's not necessarily a physical solution, it's a formal solution, because when we did the wave equation, we started with small oscillations, right? This theory of small oscillations. And if you had a pulse that was spike-like, and nothing small about that, right? Well, that's all right. So yeah, we started with the theory of small oscillations, had the masses on a chain, solution turns into, or the differential equation can be turned into this one, and the solution we see is some kind of pulse. Moving. Now, what you're going to do in physics a lot is look at so-called monochromatic waves. You guys heard that yet? And you're going to have sinusoidal waves. We're going to go right to our exponential examples. So next, let's consider u of x and t of the following form equals actually look at this, equals f of x e to the I omega t. Linear differential equation. Real part or imaginary part doesn't matter, right? We got cosines and sines right here. As a trial solution. Let's see what happens here. So we'll take a derivative du dt and equals I omega f of x equal I omega t. And then the second derivative, we're just going to bring the I omega down again, multiply with the first one, so we'll have I omega 1 squared equals minus omega squared f of x. Then what? So this was the left side of the equation. Now we have to do the right side of the equation. The right-hand side of the equation is going to be b squared u dx squared equals b squared. Oh, I forgot to write down e to the I omega t here. Let me go ahead and do that just to. Make sure I don't miss that. Okay. So b squared d squared u dx squared equals b squared. Second derivative with respect to x is just f double prime of x. E to the I omega t. So these two lines are supposed to be equal to each other. The e to omega t cancels, and we have I'll do it in two steps. B squared f double prime equals minus omega squared f double prime equals minus omega squared b squared times f. And this is a situation with second derivative equals minus a constant times the function itself. So we can write f of x is equal, let's give it some constant e to the I kx. We can match these things up here. Because what does the second derivative do? It gives us a negative constant again. So putting this together, we have k squared equals omega squared over b squared. I got room here. Oh, we'll see later. Omega equals b times k. So now I'm putting, pardon?
What about our generic constant A there?
A would be on both sides. So A is just an arbitrary amplitude constant. But what we can do is put this all together now, and this is a standard form. So what we now have is u of x and t equals k e to the I k x minus I omega t. In fact, I'm going to factor out the I e to the I kx minus omega t, and we have omega equals b times k. So this is a traveling monochromatic wave. And again, you can take the real and imaginary parts, you got your sinusoids. Monochromatic traveling wave. And you'll see these in optics all over the place. Okay, this will be your general ansatz. I'll just put as a note here, maybe we'll get to that later. If you have fixed boundary conditions, you actually generally have to take the real or the imaginary part and not this traveling wave. So this is a traveling wave in infinite space, or on an infinite line. We But yeah, I'll just put this here, monochromatic traveling wave, that's some definitions. That's not bad. Okay. I'm just supposed to come up with some homework problems for you guys. Well, I think what we'll do is maybe the three-dimensional generalization, and that'll make a nice little homework problem itself. Okay. I'm gonna erase this here. So what we wanna do is be able to, run through this little derivation here, monochromatic traveling wave. And what we'll do next is, I'll call this homework, generalize to the three-dimensional case. I'll get this one started, you'll enjoy this. So the three-dimensional case is going to look like this. U of R and T, and I'll just write directly over here. That means we're looking at X, Y, Z, and T. Is going to be A e to the I vector K dot vector R minus omega T. So the homework is to show that this solves the three-dimensional wave equation that I've given you with that del squared operator. The thing is, here we were just satisfied to have K being equal to a number, but here K has to be equal to a vector. So we need to somehow determine a little bit more about what K is. So I'm going to generalize case, prove that this equation star solves squared u dt squared equals the del squared u. How do we define K vector question mark? That should be pretty fun. And in fact, it's not going to be hard, because how do you do a scalar product like this? If I write it down, I'm giving it all away, but why not? How do you define, or how do you expand this expression out here?
X terms plus define, Y terms define, Z terms define.
So you could say, okay, that must be KXX plus KYY plus KCC. But now we have to, this is called the wave vector. We have to characterize this wave vector somehow. Where is it pointing? Right. This is the vector in the other direction. How do you define K? I'll put this here, K. How do we define K? Magnitude and direction. And direction. Okay, this is elementary, but very interesting. So actually we have a full little treatment here. I showed how to derive this thing here from scratch. We got this monochromatic traveling wave. I'll even put something here for you in red to tie it into the definition we had. You see this? You've got e to the I k. If you factor out the k, you've got x minus And this omega over k is, of course, the v. So then you have the a e to the I k x minus bt. And you see that you've got the traveling thing, because that's kind of pulse now. Again, it's got that property of just having the argument x minus bt. So yeah, but actually add these to your presentation, you know, to complete this here. Notice what I did? I had just done this formally. I got definition of omega b and k, but then when I went back my, when I plugged those back in here, I got e to the ik parentheses x minus dt, which was that traveling pulse. Good, so that gives us one problem to work on. Can we get one this week? Well, since I'm moving into Hamiltonian mechanics, but in that case, I won't get far enough to assign homework. Let's think about this for a moment. We'll just wrap this up with a little more wave material. That's pretty good. That's a good start. I'll add another one here. Okay, so I'm going to leave this up here. That's pretty nice. This I'm going to erase. So next, suppose we start with this wave equation again, and we have the material we already have here. We already know good. So next, again with the wave equation on a finite interval. Here's our x-axis, and you know, here's 0, and here is a distance a. Right, we know these were, for example, those longitudinal oscillations of the spring system. Okay. So suppose we have this is x equals a. X at t vanishes at x equals 0 and at x equals a. This would actually be that realistic case we were talking about. We don't have just infinite motion in x, but it's confined to 0 and a. So now we want to find the monochromatic solution. Of the wave equation. Yeah, so I started beginning with the wave equation. So yeah, I want to find the monochromatic solution. And what this is going to do is going to have you taking your complex exponential to the corresponding trig functions. Okay, because you need something that vanishes at 0, whose second derivative vanishes at 0 and vanishes at a. I didn't spell this right. Monochromatic. Okay. So I'm going to put this as a homework problem. Although I'm tempted to work this one. So I'm always doing the left side and the right side of this good old wave equation right here. So I did the left side, took two derivatives, my cosine, minus sine, cosine back again, minus sine, chain rule, okay? So this one we have. What are we going to have for the second spatial derivatives? Say again? What are we gonna get?
We should have negative b squared, k squared, and then just the same thing.
Yep. Cos negative t sine kx. That looks good. Are we done? Not quite. Because we need to satisfy this. So I'm gonna leave you guys with that. I recommend for both of these, just go back to everything we've done, take it from the top, and then you'll see some stuff. So we've got this little question here. This one here, we're almost done. Got one more minor issue.
We get the vanishing at x equals 0 from the sine mid.
I'm sorry?
We get it vanishes at x equals 0 from sine, right?
Yes. So we just have to get it to vanish at x equals a as well. So that won't be hard. But that actually starts to show you some various assorted things. Good. I think I'm going to leave it at that today. Let's see. Oh, you know what? I can't resist since we have a couple more minutes. I'll add one more homework. This one will really take you by the hand on this one, so this is gonna be good. The third version of this is we're going to do the three-dimensional problem. What you're gonna see is it'll build exactly off of this one. So I'm going to erase this and add one more homework problem. So homework. Now this was a wave on this finite interval 0 to a. Okay? So now we're going to have the wave equation in three dimensions. Wave equation in three dimensions. Or I'm going to write in a three-dimensional box. And I'm supposed to draw a three-dimensional box. Wish me luck. There, I did it. What we're going to do is have 0 less than or equal to x less or equal to a, 0 less or equal to y, b, c, c. So it's a three-dimensional box A, B, C. And we've got the wave equation in there. So I'm going to find the monochromatic solution of d squared u t squared equals d squared del squared u. We've got u equals 2 of x, y, z and t, and u 0, and then same for y. U of y equals b, and u of z equals 0. U of z equals c, u of c equals 0. So that means it vanishes on the boundaries of the box. You have to do this in 107T without doubt. But there's a real progression here. So if you go back to what we did originally in space, and then you solve this one, and then this one will generalize to this three-dimensional one. So that's a good set of little problems that you guys will enjoy, I believe. Okay, that's all I've got for you today. So we can talk about this on Friday too. We should do the same thing, right? We're going to start Hamiltonian mechanics, I believe, unless I come up with some other idea, on Wednesday. But on Friday we'll be able to talk about this as well. Good.